Okay, so we have completed the instrumentation aspects of planar scintigraphy. So we could now move on to the imaging equations, right. So what is the context? Okay, here this is the geometry that we are going to deal with. As discussed so far, it is probably very evident that unlike your X-ray projection radiography, the source, right, in X-ray projection radiography, the object was there, source was on one side, the detector was on the other side. Here the major change in the geometry is because of your source is inside the object, right, in that sense. So this is your source and this is your detector. So we will use the same x and y for in plane and z dimensions to relate to the depth, right, or the source detector distance. Okay. So as you would see, what is the paradigm that we are looking at here? See, it's a probabilistic thing, right? So you give the radio tracer, the radio tracer is going into the body. So now the source can be anywhere in the body, right? It is circulating. So you have radioactivity come out. So after it comes out, the radioactivity can essentially not leave the body, right? It can still get absorbed inside the body. That is one possibility which happens. Then it may get, so here it doesn't come out of the body, or it may come out of the body like these cases, but it can actually go in some other direction where the detector is not there. Okay. So that is again a chance for that. So if you account for all these chances, even after you have the radioactivity distribution, only a portion of it which actually comes on the same side of the detector has a chance to go to the detector. Even there, right, there could be, it could probably go in direction which is not, hitting the detector perpendicular, right, in this manner, right. So remember, we had collimator, and therefore the collimator is looking for straight line of sight. So even though D might go, all likelihood the collimator will not take it, right. So if you write our imaging equations, we will have to consider that we are going to use a collimator, and therefore only straight line paths are going to be used. And in this geometry, if you notice, there is a chance radioactivity is distributed everywhere, right, 3-dimensional here, but there is a certain portions that will come and hit the detector, and we will assume that only those that are coming parallel to your z axis, parallel to your collimator, right, where there is hole, only those are going to fall on the detector and make its way to the image. So what we have here is a radioactivity. We will denote it by A of x comma y comma z, right. This is same denotation we used earlier when we started with the radioactivity. And another important aspect here, we will consider monoenergetic photons with energy E, which is not unreasonable, right. We talked about certain tracers, and one of the desired aspect of a tracer is to give out a particular energy. So this is going to in some sense make our life easier compared to our X-ray projection, where you could get spectral. And very intuitive from here, because of the collimator that we have talked about, we will assume that only it's along the line, right. So only along the line, so parallel to z axis is what you will get the radioactivity into the detector. It will not come at any angle. So we have arrested the Compton scattered ones, right, because of the collimator, and so we will not worry about that. So now how do we write our imaging, right, equation? Given this scenario, what is our imaging equation? In some sense, it is very similar to what we did for projection radiography, right. you could think about how we came up with the first equation for projection radiography, right? And then we simplified that for CT, used mono energetic equivalent, and so on and so forth. So here is very similar. Radioactivity comes out only through the line it come, that hits the detector. So we will try to first start with what we know, right? Before we jump in, one clarification: in X-ray, when we did, we were interested in writing everything in terms of intensity. Whereas here we will make switch gears, we will write the equation in intensity as we know from before, but then subsequently switch over to your fluence rate, photon fluence rate, because here you are interested in radioactivity. Okay. So that will be a small switch. Instead of I, we will write the I and appreciate how it is similar to what we had done for projection radiography, but then switch over to your photon fluence, right. So this is what we will do. So if you have the Anger camera, the equation, you can write the intensity as radioactivity into, so number of photons, right, into E, energy per photon. So this would be your intensity falling on the detector, where R is just the distance from XYZ to your location on the detector, right, X, Y, XD, YD, 0. Okay. So that is from the source to the detector. So you will notice that there is this 4 pi r square. So this is a inverse, right, inverse square law, remember. So nothing fancy. So we have done this before, but again we said we will not worry about intensity, we will switch to photon. So we will replace intensity with photon. So we can write, right, we can, this is not a big deal, right, we have energy, it's okay, we will start to write in terms of only A. Okay. So that is fine. So we can quickly change the equation. Instead of photon intensity, it can be number of photons, but along the line we will also incorporate. What do we want to incorporate? Attenuation. What do we mean by attenuation along the, the source is right somewhere in the body. So when it is trying to come out, it is to cross certain part of the body, right. Of course there is also medium before it hits the detector. So in general you can incorporate a attenuation, the radioactivity is getting attenuated. So we can also incorporate that between XYZ and when it hits the detector, XD at 0. Okay. So if we do that, we can write your phi d, instead of I we are writing it in terms of phi d, photon fluence, as A by 4 pi x pi r square exponential of your attenuation coefficient along the line 0 to r, right, clear. So this is exactly, I mean, very similar to what we had for X-ray photon, we wrote it in intensity before. Okay. So nothing surprising here, but then this looks okay, right, but then we need to, as we go along we will do this again and again repeatedly. It looks very similar, but there are subtle changes that we should appreciate. Okay. So even this we can kind of simplify further, because we said we are going to be interested in parallel hole collimator. So if it is coming at some angle, right, we are not really interested in that. We will pretend that that is not going to contribute to image. It is going to be arrested by the collimator, absorbed by the collimator. And so we could, instead of having R, right, instead of having R, we can have only Z, right, along parallel to Z, right, collimators are parallel to Z. So we could write phi d as, instead of R, only along Z you are going to have everything parallel to Z, right. So your A by 4 pi Z square along Z is what you are going to have the attenuation. Okay. So it is not going to come at some angle. So this is your, for parallel hole collimator configuration, this is what is falling on the detector. You had a source and the source is attenuated along the line, and this is the radioactivity that falls on the detector after going through the collimator. Okay, after going through the collimator, what is there? Crystal. Okay, so we will come to that. So this is what at least you have let in, okay, into the camera. Okay, so is this good, or is there some simplification we can think about? Well, before simplifying, we will have to see whether it is generalized, right? So now look at what is this A. Oh, A is a radioactivity, that is fine, but A is what? A can be anywhere, right? A is a function of x comma y and z of the body. It can be front of the body, back of the body, it can be from the head, it can be from the toe. So it is distributed. So A itself is a 3-dimensional, right, distribution. So we'll have to first upgrade the equation and then see how all we can simplify. Okay. So photon fluence on the detector, right, that is what we are talking about, is phi of x comma y. So what we have now, we have made it little more general. A is x comma y comma z. Of course it is rest of it is fine, right, rest of it is fine. Of course you have made this along z from before, right, only along the line of parallel to z, only parallel collimator, right. So parallel hole collimator. So this is fine. So we have now basically said whatever is falling on the detector plate x comma y, detector plane, right, is whatever happens from the source along the z. You have the integration. Of course there should be a dz here. Okay, there should be dz, because this is going over minus infinity to 0. Okay, a x y. So there should be a dz. I will update the slide, but okay, so there should be a dz. Okay, so the idea is, yeah, you have along the line, right. So you have a thickness. So a, x, y, z is the source distribution. Well, it looks very similar to your projection radiography, nothing fancy, nothing fancy, but only difference is, of course this E can go, this actually in the projection radiography it was little more complicated. We had another integral for the energy levels, right. Of course when we started, we conveniently said source is a X-ray tube, so IS was in double, whereas here that integration is not simplified. So we get something simplified, but certain other things are not simplified. So you notice two effects here in depth dependent, which are depth dependent, right. One is your Z here appearing. So therefore your source, when it falls on the detector, you have a depth dependent effect, which is kind of we are familiar with this term. But what is important that we didn't explicitly see before is this guy. This is depth dependent as well, naturally, right. So whether the intensity, the radioactivity is in the front of the body or back of the body, right, whether it is close to the detector or far away from the detector, is going to have an effect, because all of this is going through the same attenuation as well, right. So you look at it, the Z appears both here, which is your depth dependent effect, and here, right. So you have object dependent attenuation, right. So this is basically what is this depth saying. You have some activity in the front or back, means it is going to travel your mu, right, your mu. So depending on whether there is more material in front or back, the path, along the path, that is going to have an effect as well. Okay. So this depth dependent effect, this is a straightforward one which we knew from before, inverse square law. but you have object dependent attenuation, right, object dependent attenuation mu, and therefore whether the source is more inside the body or more close to the path that the radioactivity, right, the photons should travel, right, along the mu is a function of, right, the depth dependent or object dependent attenuation. Okay. So, there is object dependent attenuation, these two contribute for depth dependent effects. So, in other words, you could have the same radioactivity from the same Z, right, but at different locations. In one location you have more tissue to travel, more mu, in other location you have less mu. So, what is hitting the detector will be different, even though the starting out radioactivity was same. Okay. So, it is dependent on that. So, one thing we can try to reduce, simplify. Okay. So, this is good. So, why do not we consider a planar source instead of having this 3D source? Can I have a planar source? In some sense, why worry about the Z, right? Why cannot I collapse that to the plane of where the radioactivity is? So, we can collapse that and have only a plane. Therefore, the front or back, at least to that extent, I can simplify. How do we do that? Well, the same delta function, right? I have a volume, I have to take a plane. So, essentially you are picking a Z plane, right. So, you can write your 3-dimensional A of x comma y comma z, you have some at z naught. So, say at the center of that you take A z naught, you have a plane now, A z naught, because z naught is your delta function. So, from z you have taken a location z naught. So, at radioactivity A z naught is radioactivity at z equal to z naught. So, you are taking a plane. So, now your 3D source, radioactivity source is made into a planar source at location z equal to z naught. Okay. To some extent this seems to simplify, because at least one integral I can get reduced, right. So, I can reduce that at least. So, now I have my phi of x comma y as A z naught. So, this z is gone, right. So, that is this integral that is gone. So, you get this equation. So, this is reasonable. Couple of things that we need to appreciate is, now it looks very similar to your projection radiography, but for one complication, which is, so this is straightforward, right. This is along the path whatever attenuation is there, inverse Z. Before we used to worry about, we could integrate this into a IS, and then we set that as I naught in our equations. Here we have your source is still x comma y, it is planar, it is not one point. Remember, in X-ray we had similar equations, but we had a point source and then we had an extended source, the effect we incorporated. But for all practical purposes we started with a point source, whereas here the source is a planar source. Okay. So, that is one thing, and you also notice that it is a tricky business in even though it looks okay, we can comprehend this, it looks little tricky in practice, because even if I have a planar source, right, even if I have a planar source, so the radioactivity is distributed uniformly in a plane. For example, I have the detector, right, your planar source could be there, but then your attenuation along the path could be slightly different. Okay. So, all this will play a subtle role in explaining or interpreting the image. Okay. So, that is for planar source imaging equation. So, this is a good point. So, what do we need to do? In projection radiography we had imaging equation, and then we ended up, oh, this is the imaging equation, and then we studied the image quality. And in CT when we did reconstruction, we started with this and then we talked about customized it for the instrumentation of CT, and then we did the reconstruction. So, similarly here we have the parent equation. Okay, when we go to T, which is a SPECT or PET, corresponding instrumentation, we will start with the imaging equation and try to go back and estimate. Okay. So, we will now talk about image quality in scintigraphy. Similar, what are the parameters we are going to study? Image quality is resolution, noise, signal to noise ratio, contrast to noise ratio, right, similar things. But what is going to be different here? Well, the parent definition is going to be similar, but the instrumentation, the physics we saw to an extent we know, we will draw similarity with what we have covered in projection radiography. But then what are the unique aspects here? Well, the unique aspect in some senses, it is the radioactivity that is counted, and you have a scintillation screen and photomultiplier tube, unlike projection radiography where we had an intensifying screen and the image was formed on the X-ray film. So, there is lot of similarity, but then there is also some differences that make this the equation slightly different. So, first we will talk with, when we talk about resolution, when we talk about image quality, in that we want to talk about resolution. Collimator resolution is one thing, because we have this collimator for what? Oh, so that you can avoid Compton scattering, right, avoid Compton scattering, that was the idea. So, the idea is if you have a point radius activity, right, we talked about parallel hole configuration of the collimator. So, when you have a point radioactivity, when it falls on the detector, right, it is going to be spread out, okay, it is going to be spread out. So, the idea is we could define resolution as a point spread function for this geometry, okay. So, what we have is, we have the crystal, right, in front of that you have the collimator has its configuration, right, a length, a height. So, you have a point source at some distance z. So, if we call this, right, you call this, so you have a point, if you call this RC of z, a resolution collimator of z, so 2 times this is the full width, right. What is the definition of resolution we have been using? Full width at half maximum, okay. So, if we do the geometry, right, and solve full width at half maximum, we get collimator resolution to be d by L in terms of the parameters that you see here, d by L of L plus B plus Z. What is striking here? So, RC of Z is nothing but your full width at half maximum, okay, half the maximum width at point source at distance Z, right, without being absorbed by the collimator. So, it can go here, right, it can go through, okay. So, this is your full width at half maximum of the point spread function of the detector of the, right. But what is important here? Oh, you notice this RC or resolution is a function of Z. What does that tell you? Oh, that means whether I have the object close to the detector or far away from the detector, that is going to have an influence on the resolution. So, the system resolution is not really system resolution, right, the collimator system resolution, it is not like that. The collimator resolution, what we call, is dependent on where you are going to present the object, okay. So, that is the important message. So, if your Z is more, RC is more, that means the spread is more, that means it is poor resolution, right. If Z is less, the spread is less, better resolution, okay. So that is a key aspect in collimator resolution. So how else can you do better? Oh, I can kind of increase this L. If I increase this L, right, I can reduce RC. Okay, but what is the challenge? If you increase L, I am going to be more, right, I am going to be more taller. So I will be very specific. So sensitivity will get affected. So we will talk about that little bit later. So the point to note is RC is a function of Z. So targets farther away are blurred more. Okay, so this is a key point, otherwise it is fine. Also you notice L increases, RC reduces, right, L increases, RC reduces. That means L increases means your resolution is becoming better. But what is your downside? Sensitivity. Why? Because if it is becoming taller, right, you are going to reduce the number of photons that can come through. Remember our, very similar to our grid ratio that we talked about. I mean the variables, the same B, H and all are used, but go look at that, you know, that was in a different context, right. So here if you notice, your resolution is, you can design your collimator but with a trade off. Okay. But for a given collimator you can sort of play with the resolution and sensitivity by arranging the object or placing the detector, move the detector close or far from the object. Okay. So how do we incorporate that? How do we incorporate this knowledge? Okay, all this is fine, we understand. Your linear systems theory we did. Okay, you had the imaging equation. Now you convolve that with the point spread function of your collimator. Okay, so this is HC is your system response or whatever, right, of the collimator. C is collimator and it is x comma y. So here usually it is a Gaussian, which is what is assumed. Okay. So this is a reasonable model, a Gaussian model is typically used and you can incorporate its effect. So the imaging equation is now incorporating the blurring due to your collimator resolution. Okay. So is that all? Is there any other resolution that we are worried about? Because we are interested in the image. The collimator, after collimator what is there? You have a scintillation crystal. Even in image intensifying screen we noticed that there was a effect of thickness, right. So here that means that should also have a part. Okay. So we call that as a intrinsic resolution. In fact, subtle point, intrinsic resolution, when we say, right, what is coming to our mind is, okay, we know this is all parameters, no doubt about it. So thickness of the crystal, what do you know about that? Oh, thickness, we did not allow the Compton scatter to enter from the object. So only straight line came through collimator, but after it comes through collimator, right, it may have Compton scattering in the crystal and therefore some will probably go on further into the photomultiplier tube and that will get detected, and therefore you will still have Compton scattering effect on the output of the photomultiplier tube, right, which is what is going into your imaging equation, image localization, right. So, so that could be a problem. So thickness of the crystal has a similar effect, but the Compton scattering, right, that spreads the light out. Okay. So you have Compton scattering from the crystal point of view. So it goes into the crystal, interaction there, some amount is gone. So you could also have noise, right. So noise, all that. So what you are going to get hit, right, on the photomultiplier tube, output signal. Output signal is from the photomultiplier tube output. That is located, say if it is a frame, you put the pixel x comma y comma z, remember. So, intrinsic resolution, even though you kind of know that these are the factors that have to be taken into effect, the intrinsic resolution actually kind of comes along when you do this x comma y, right. We talked about localization. We have photomultiplier tube, we calculated the z pulse, and then we did the center of mass, if you go look back, to say where it came from. That calculation of your xi comma yi, right, that can get corrupted because of all this. There could be uncertainties in that because of all this, and that, right. So, therefore, that resolution to the precision with which you can localize, that is your intrinsic resolution. So, it is essentially your xi comma yi. Remember, we did what we called as localization, x comma y. That is where you have the effect of intrinsic resolution. Okay. All this contribute to that. Okay. So, in some sense, this is slightly different from your projection radiography, because in projection radiography, the intrinsic resolution or equivalent of this, if you really look at it, the thickness of the intensifying screen had a role in spoiling the optical film. That is it. We could not recover from that. Okay, it was directly the point spread of the of the intensifying screen that directly had an effect. Whereas here, this point, right, the point spread similar to there, that is not directly recorded. The point spread goes and hits probably multiple photomultiplier tube. So, you get the raw signal out, and then you use all this signal to calculate the x comma y. So, you have some sense that you can come up with some techniques to reduce that. So, the resolution could be better than what would be a regular point spread alone in your projection radiography, right. But so that is the difference, but it is similar in that sense that the same effect of thickness is going to have. So, here also we will model it as a Gaussian. So, intrinsic will also be modeled as a Gaussian. Okay. So, these are all things that you can calibrate, right, for the instrumentation. So, you could do that. So, we will now update our planar source equation with all the terms, a z naught by 4 pi this term, exponential, and the 2 blurring. Okay. What else? From a resolution point of view, that is done, but we still need to talk about something called as sensitivity, because we kind of even mentioned that. What is sensitivity? It is the fraction of photons on an average that pass through the collimator, right. So, the configuration of our collimator is, if I have length, right, we talked about more length of collimator, increase the L, we could reduce the R or improve the resolution. That is what we noticed. That time we said no, you compromise on the sensitivity or the efficiency of control. So, you notice that is because if you do this, right, sensitivity is what? Fraction of photons that pass through the collimator for each emitted photon directed at the camera. So, if you increase the L, your resolution is improved, but then there is a good chance that it is going to be very specific. It is not going to let anything come at certain, because it will hit the lead. If it is tall, right, there are fewer acceptance angle. Therefore, the number of photons that are going to come through and hit the detector after the collimator is going to reduce. Okay. So, your detector efficiency, collimator sensitivity or efficiency is roughly worked out like this, where k is approximately 0.25. Okay. So, there is lot of, so this has to do with your material property. They try to increase the thickness. Remember, same idea, material property for a given energy thickness, all of this has to be controlled. Okay. So, in some sense, when you have a radioactivity, when you do the radioactive tracer, when you engineer that radioactive tracer, you have an energy band, and then you engineer the detector, you write everything on the detector side, angle camera side, you make everything specific or as much close to the best case scenario for that particular energy, right. So, in that sense, it is not like one detector fits all kind of thing. Each imaging study, each patient, right, at least the physiology that you are going after, all that requires a proper choice of what detector you are going to use. If you are going to use a gamma, high energy gamma for a particular study, then you need to change your scintillation crystal. So, your camera detector side has to be changed in tune with what you are going to do. Okay. So, detector efficiency in some sense is going to be dependent on all the factors that we have talked about. So, there is no formulation per se, but you understand all this is when in a center they do lot of studies, they may have all these calibration values so that they can kind of use an appropriate setting to do the imaging. So, it depends on the study, right, what aspect, so the radio tracer and the settings that they want for that radio tracer, all this they will have to handle. Okay. And then you get the once you get the x comma y z, we talked about what image is shown, right. Okay. So much for image quality with respect to resolution and detector efficiency. Of course, we need to talk about noise. If we talk about noise, we talk about signal to noise ratio. When we talk about signal to noise ratio, we need to talk about more importantly the contrast. But here, as you would notice, nothing much has changed, right. You get n photons, only thing is it is in the gamma energy range. So, the photons arriving at the detector, you have the same Poisson's ratio. So, in some sense, the signal to noise ratio, right, in one detector, if you will, is going to be what mean divided by standard deviation. Mean is going to be Poisson ratio, standard deviation therefore is going to be square root of that mean, and therefore you are going to have, and these are all number of photons, right, average number of photons that are coming. Only the energy is different, otherwise the same thing that we did for projection radiography as well, right. So much is fine, but there are subtle difference. So, I will just show that in one. So, it is very similar to your X-ray imaging. So, you can get your, because of your Poisson distribution that we saw, intrinsic SNR is square root of n, no big difference. What is the context here though is, here you have a detector. When we talked about detector, especially if you talk about that frames like static mode, right, we want to talk frame detector mode. What happens? We talked about having pixels, right, some j cross j pixels. Okay. So, now if it is having j cross j pixel, if you look at per pixel, right, so mean of the detected photon. So, here that is the difference, right. So, here when the photon comes, right, even if it is spread, the photomultiplier tube, it gets picked, and we are calculating, we are adding all that. So, we are calculating the z. So, what comes here comes out, maybe it is spread out, and therefore, we are trying to localize it by calculating z pulse and having the threshold and doing all that. So, in some sense that is fine, but per pixel what happens? So, mean detected photons, if that is n, you are going to have that over j cross j, right. So, it is going to be mean detected photon per pixel is going to be n by j square, and therefore, your intrinsic SNR is going to be root n by j. So, this is the slight contextual difference to your SNR per pixel in your scintigraphy. But why is this important to highlight? What this says is, You might intuitively think, oh, if I have 256 cross 256, it will be better, I mean, or 512 cross 512, right? I might be better if I am given a choice between 256 cross 256 and 512 cross 512 or 128 cross 128. You would think, okay, the more the pixels, right, I would go for that, right? You have better resolution, you would think, so you want to go for that. But what is the downside? Your intrinsic signal to noise ratio goes down. So there is no one solution, because I mean naturally, right, your detector size goes down if you increase the number of pixels. So your localization is better, but then your number of photons that is reaching is less, and therefore your intrinsic signal to noise ratio goes down. So it's a trade off. Okay, so there nothing is, like I say, in imaging cutting, that is one commonality between amongst all the different modalities. There is no easy way out, there is no easy solution, there is always going to be this compromise or trade off amongst the various parameters of image quality, okay, with the various physics. Some are physics limited, some are instrumentation, complexity, but there is a inherent trade off. That is what is important, you try to understand, okay. So that is, otherwise the rest of it is very similar. So you can have a contrast signal to noise ratio, remember we talked about this, and pretty much the same derivation, you get C of square root of NB. So there is now big difference in this part. So this kind of completes the scintigraphy that we wanted to cover. I know it was a quick coverage, but this is at the level of introduction to the subject, right? There are intricate details that you may want to jump in and read and study, especially if you are from, say, material science kind of background. You may have lot more to do with development of crystals and the converting the efficiency and so on and so forth, okay. But otherwise I think this is giving a good start. Our next agenda is, okay, it is equivalent to our planar radiography, right, analogous to your, in X-ray we did projection radiography, here we are done planar scintigraphy, right, there we did computed tomography. So here we should also get some tomography, right. We have collapsed the object A, X, Y, Z, we have collapsed, but in reality we would like to know where the radioactivity is along the depth, right. So if we take a particular cross section, we would like to know where the radioactivity is along that Z. Right now in planar scintigraphy, that is lost. All we know is maybe the radioactivity is coming from the head or chest or abdomen. You really do not know whether it is from front of the abdomen or back of the abdomen. You do not know which organ there is accumulation. Okay, so we need to naturally go towards tomography, which we will do in the subsequent lecture. Thank you.